This is lecture 16, and lecture 16, we're going to take a break for one lecture from our unsupervised stuff to talk about, to go back to our kind of supervised regression techniques for a second. So we only got one lecture into unsupervised techniques, but principal components analysis is such a centrally important topic to all of mathematics, all of statistics, all of machine learning, that it's worthwhile taking out one lecture and talking about how, in some ways, it relates to some of the previous things we've talked about. So this lesson, this lecture is titled PCR, which stands for Principal Components Analysis Regression. Or sometimes people just call it PCR, Principal Components Regression. And by its name, it is a regression technique, and it is a regression technique that uses principal components, right, principal components analysis. And so it is going to relate in some really nice ways to kind of the variable selection topics that we've talked about. So we should do a real quick recap here about PCA. So we had started talking about not supervised, but unsupervised techniques. And unsupervised techniques are basically trying to learn interesting, important patterns in the data, but there isn't a distinction between X's and Y's. We're trying to predict some Y, we're just trying to summarize or learn the important patterns in the X's. And not surprisingly, these unsupervised techniques, if we kind of summarize the data in a useful way, it can be used then down the line in a supervised technique. And PCA regression, or PCR, is one of the easiest, most straightforward ways of viewing that. In particular, the first kind of class of unsupervised techniques that we were learning was dimensionality reduction. And the idea here was that we want to take our set of original covariates, x1 to xp, and through some magical procedure, we want to create a new set of covariates, z1 to, let's say, zq, where q is much smaller than p. Thereby, we go from some p dimensions to some q much smaller than p dimensions. And so we have reduced the dimensionality. And PCA, one of its goals, it is a dimensionality reduction technique. And the particular way that PCA operates by creating these z's is PCA will summarize. Oh, that's supposed to read summarize. Summarize the x's into z's that are linear combinations of the x's. So z, j, let's say, is the sum where I goes 1 to p of some weight, let's say z w ij times x I. So something like that, right? The z's are just the linear combination of the x's. We can write this, since we all taken linear algebra, in a really simple way, where our new matrix of covariates, or a new matrix of features of data, can be written as our old matrix x times some weighting matrix w. And this weighting matrix is just encoding these w's. And so the idea is that we create a new data matrix with still n observations, but q variables, q columns. and that is created from our old set of covariates, our old data matrix, which has p columns. So this is n by p. And of course, to get there, we need our W matrix. That will look something like this. And that is going to have to be P by Q. And each of the columns, we'll call them W1 to WQ, is going to be one of our weight vectors. So you could summarize ZJ as the inner product between, it's like X times WJ, right? Where WJ is our weighting vector. So that's some nice notation. And so PCA is not only going to do this dimensionality reduction, it's going to do it by summarizing the x's into linear combinations and create some new z's. But the third goal of PCA here is going to be capture as much, quote, information in the original x's in the new z's, and here information is equal to basically variance. And so we're going to try and create the z's in such a way that they have maximal variance. Here we consider variance in our data to be interestingness. It's just the ways in which our data is kind of spatially spread. The way in which it fills up the space is basically some kind of measured by variance. And so in this framework, we get our weight vectors. W1 is going to be the weight vector W, and that will maximize the variance of Z1, right? So Z1 here, so right, Z1 is X by W1. And so we're going to choose the W that maximizes, this W1 is going to be the one that maximizes the variance of this thing. And we're going to have this constraint here that W1 is a unit vector, because if we don't constrain these W's, there is no maximal variance, right? Otherwise, we could just say something like, you know, the variance of, you know, 1000 XW would be 1000 squared variance of XW, right? And we could just keep choosing a bigger number, 2000, 3000, right? And you keep getting larger and larger and larger variance. If you don't constrain the maximization problem, there is no maximum here. And so you have this kind of constraint, but that's not a real super important constraint here. The more interesting constraint is that our second weight vector is basically going to solve the same problem, where it's going to maximize the variance of Z2. So it's going to choose some weight vector W that's a unit vector to maximize the variance of Z2, subject to the constraint that the correlation between Z1 and Z2 is 0. And so this correlation, this constraint that they be uncorrelated, that our Z's be uncorrelated, means we don't capture same information. The idea is we are parsimoniously reducing dimension, right? So if you create Z's that are correlated, they contain, and so correlation is basically a measure of mutual information. If they're kind of correlated, then you're not most parsimoniously reducing the dimension of space. And our goal ultimately is to capture as much info in the smallest number of variables. And so we don't want these things to overlap, so we constrain them to be uncorrelated with each other. And I'll just write out, you know, the third one. You can calculate a bunch of these components. And the third one can be similar. We'll maximize the variance of the third Z, but it's going to be uncorrelated Z. Correlation between Z1 and Z3, and the correlation between Z2 and Z3 is 0, etc. Right? And so you can get these higher and higher components. And so and that will allow us to get higher and higher number of principal components, these z's, by getting these weights. So that was basically the procedure. We should note here, so the solution to this whole thing was that W is, if I just take off the first Q columns of my SVD, so W is the first Q columns of of the V matrix for my SVD, where my data matrix has a singularity decomposition UDV transpose. So we just take this V matrix, we take the first Q columns, and our new Z matrix basically is going to be X times these first Q columns. And that's the whole game. And so in some ways, PCA is just a renaming of the singularity decomposition. I mean, that's basically what it is. And it just shows that this mathematical concept, the SVD, is kind of really centrally important. Typically, for PCA, although there's no hard rule that says you have to do this, typically we, one, center the x's, let's say mean center, so we subtract off their means, and two, sometimes, not always, but sometimes we rescale the xj's by their standard deviation. Now, that's not always necessary. The reason you might want to do that is, so first of all, the SVD is sensitive to both the column means of x and the scales of x. So we'll get different answers if we do this. So it's not a scale invariant procedure, unfortunately. And the reason you want to center the x's, it's actually not that big a deal. If you don't center them, typically the first principal component will just be the mean, so it's not a huge deal. If you don't rescale them, if we have features that are on massively different scales, our goal is to kind of maximize these things, and we're maximizing basically a linear combination, right? So we're maximizing the variance of this linear combination. If some of the x's are on a bigger scale or have much higher variance than other x's, then those are going to be kind of preferentially weighted, because choosing those, if they have higher variance, will give us a higher variance, and that's what we're maximizing here. So that might be something we want to do. It might not be, and so it's something to pay attention to. Sometimes the variables are all kind of similar. Okay, they're all kind of on similar scales. We don't need to rescale it. If they aren't, and one's on grams and one's in kilograms, well, if we don't rescale those, PCA is going to preferentially weight to our variables, our principal components, to include that kilograms one, because it has a higher number just by raw numbers. Or maybe guys with the grams, you'd be higher numbers. So preferentially choose the grams, right? Because it'd be 1,000 grams, right? Which is what 1 kilogram, right? So, and that might not really be what we want to do. That might be kind of artificial, and it might, it might just lead us to doing some weird things. And sometimes it's like, if it's bad enough, the first component is just going to pick out the variable with the highest variance. It's going to put all weight on one variable with highest variance. Well, that's not necessarily what we want to do. That's a kind of degenerate version of a linear combination. So oftentimes that we will rescale these, but recentering, that's fine. It's not a huge deal. And rescaling, that's a kind of art thing where, sometimes you want to, sometimes you don't, but you really need to be aware that there can be issues there. So I want to mention one more interpretation of PCA. There are about 1,000 different ways to interpret this procedure. And, we had said that PCA is trying to maximize the variance of the principal components. The other way to view it is you can view it as minimizing how much information we lose. So, right, so one way of viewing PCA is if these are by 3 coordinate axes and I have a bunch of points in some space here, and PCA is basically going to find the subspace of this, and my weight vectors are basically going to define my weight vector. So that'd be like W1, W2, and W1 will basically tell us, so maybe I should draw it something like this. So if the data is kind of maximally varying in this one direction, so it's maximally stretched out, that's what varying would mean, that's going to be W1. And then the second most maximally stretched out will be W2, and the third most, etc. So that's kind of the picture we could get. And ultimately, you know, we are basically project, if we look at X times this V matrix, or we look at these Z's, these are basically the coordinates of our original data projected into, let me write this another way. Let me write it this way. So if we project our data onto this subspace, the Z's are the coordinates with respect to the basis of this space. And the basis of the space are the W's. So that's a kind of very geometrical linear algebra way of interpreting this. And we could instead look at the projected data in the original basis of the space. So, you know, so this Z's are basically the coordinates in this subspace. So in this subspace is, you know, is a 2-dimensional subspace. I'll have 2 coordinates, say. I go down from 3 to 2, so I'll have 2 Z's. But you could also take any point here, and it would have a 3-dimensional coordinate. So basically ignoring kind of the orthogonal, you know, direction, the direction orthogonal to this plane. But you could, you know, you could get those coordinates too. And that would be if we projected down onto the W matrix of our X. I actually probably want to write it this way. So if our projection operator, we project down, and there's a couple ways you can view this. It would be X by V1 to Q, V1 to Q transpose. So this is basically our projection onto subspace. You notice here, these are the coordinates with respect to the subspace, and if we want to go back up to the coordinates with respect to the bigger space, we just multiply by V1 to Q transpose. This, the reason we're multiplying by the projection matrix on the right, when normally you'd multiply on the left, is because we're projecting the rows rather than projecting the columns. This matrix is, oh, I don't know, we could call it XK. I'm sorry, XQ. So it's kind of it's what we get when we project down with the first Q principal components. Alternatively, what you would do is if, right, so X has SVD, U sigma V transpose, XQ, you could write as U 1 to Q sigma, say Q times V 1 to Q transpose, right? So where I take the first Q columns of U, the first Q columns of V, transpose it, and this sigma, I was calling it D, wasn't I? I was calling it D, and I'm just going to have the D by D, the Q by Q Q by Q upper submatrix. So basically, if I truncate, this is sometimes called the truncated singularity composition, where instead of calculating all of it, I just stop at some Q that's less than the rank of this thing. And so that's another way of writing it. And you should be able to see that if I that this should be equivalent to my other way of viewing it. Yeah, it will be, right? If I multiply by this projection matrix, if I multiply by B, 1 to Q, and then B, 1 to Q transpose, basically, I'll just get this whole thing back, because those V's are going to cancel out. So that's another way of viewing it, and this is called basically it's like a truncated version, you know. Remember that, or recall, or notice, I have up to, you know, R, which is the rank of my X, possible principal components, Z's, right? I can only calculate R of these where R is the rank of my matrix. And if I set Q to be R, I get back my original matrix. Right? And if I set Q to be less than R, I'm going to get some kind of reduced fidelity version of this thing. So if you want to, say, compress an image, one way to do this is you do exactly this. You do the SVD, and then you truncate your singularity composition after a certain point. I think I should show that in lab. That's kind of a cool little procedure. You get basically a reduced fidelity version of the image. And so, again, when we're talking about PCA, right, and I'm talking about how I'm calculating, you can calculate up to R, which is the rank of X of these. And you can never have more than that, because once you calculate R of them, you have recapitulated your whole matrix. Okay, so what does this have to do with our second kind of interpretation, which is that we want to minimize information lost. And I'm not going to go through a whole proof of this, but I'll just summarize it by saying there's something called the Eckert-Young theorem. And the Eckert-Young theorem says that if I want to minimize overall matrices B, where the rank of B is some Q, if I want to minimize the difference between my original data matrix and some other matrix, right? And we're going to measure the difference with the F norm, which is our just sum of the squared differences of elements in these matrices, right? So if I have a matrix A and I take the F norm, it's just I sum over the rows, I sum over the columns. It's supposed to be J of AI J squared, right? I guess you take a square root there. It's just kind of like a Euclidean norm. If I want to find, you know, so if I look at the difference between X and any other B, now X might be high rank and Q is lower than the rank of X. So if I want to say, maybe I want to find, so we get the argmin over this. That is, what's the value of B? What's the matrix that is closest to X in this sense, but is rank Q? Where Q is less than R, or rank of X, right? What's the closest rank rank Q version of X? The closest matrix that's rank Q, but is closest to X. Well, what's the answer? It's XQ. Not maybe too surprising. The proof of this is actually very, very similar to the proof that we went through last time, so I won't go through it. But the idea is that this is like minimum. If I use, say, xq over x, so I reduce the dimension or reduce the rank of this data, what do I lose? And it's measured right? The difference is basically the difference between those. If I use b over x, how much do I lose in terms of the difference between these things? And if you measure it that way, and you ask, okay, what's the b that will lose the least amount of information of all b's that are ranked q, turns out truncating the SVD after q terms is exactly the thing to do. So that's called the Eckert-Young theorem, and it's another way you could motivate this whole problem directly from that. Okay, so let's get to the main topic of the lecture here. Now, we're 25 minutes in here. And the main topic is principal components regression. Let's say PCR, PCAR, whichever you want to say. And the idea with PCR is that instead of regressing y onto x, which is n by p, let's regress y onto z, which is, of course, n by q. So this is basically variable selection? Question mark? It's not quite selection, but it's reducing the number of variables we have, right? So here again, q is going to be chosen to be much smaller than p. So the idea is, if I wanted to do a variable selection, maybe I don't even have to do variable selection. Instead of picking individual variables to remove, let's just find a condensed representation of x, called z, using, I don't know, PCA. It's probably the best technique out there to do this. It's provably by the Eckert-Young theorem the best way to do this. And regress y onto z instead. And this is PCA regression in a nutshell. That's basically the whole story. So let's talk about it in a little bit more detail, just to make it a little more clear. So typically, we're going to assume here that, let's just write out the steps for PCA, for PCR, principal components regression. And let's say one, we're going to assume that our x's have been centered, have been mean centered. So that the mean, the kind of empirical mean of just sum up my x, the observations of xj, divide by n, that thing's going to be 0. Optionally, for the reasons we discussed before, you could rescale by the standard deviations of the xj's. And many of these procedures will do that. Now, I'll mention ridge regression first now. Something like ridge regression or lasso also typically do this. Now, the centering doesn't matter as much, but the scaling does quite a bit. I guess the centering matters a bit too, but they both matter because in those cases, we're penalizing all of the betas in a similar way. We're taking the norm of the vector. So in the same way, if one of my variables in a different scale, right, the beta would change correspondingly to that scale. And so if I have things on wildly different scales, my lasso or my ridge regression is going to pay attention to those variables more than the other ones, and that's probably not really what we want. So actually internally, most of the time, and there's often an option in the software, it scales things and then kind of undoes it when it does the predictions. You don't really notice that it does this, but it does. But for the sake of this discussion, let's just assume their scale. Practically, when using software, it takes care of it for you, but you should understand what's going on. So I'm just going to make that assumption, and we're going to let X be our covariant matrix have singular value decomposition, UDV transpose, right? Now, this is equal to PCA, basically, right? If I've centered and rescaled optionally my variables, then those V's basically give me my weights. And so PCA is in some sense giving us the Z's. Notice here that since V is equal, or V1 to Q is equal to W, and right, generally XV is equal to UD. Now D is a diagonal matrix, so it'll just scale the columns of U. And so this thing, this U, so U1 to Q are basically my Z's. Oftentimes people interchangeably talk about the Z's or the U's. They're basically the same thing because it's just the U's scaled, and sometimes you don't even want them scaled. So all the Z's are basically the columns of the first column of U is basically the first Z, but then you got to scale it by whatever that first singular value is in the D matrix. But so PCA is basically just this decomposition, and you look at different parts of the decomposition, you see different parts. You want to see the weights, look at V. You want to see the components, you look at U. Or the Z's, you look at U. You want to see how those things should be scaled, or what the relationship is, or what the variances are, and you look at D. So it's kind of a really compact notation for all the parts of PCA. Nonetheless, the idea is that, right, we have X has this SVD, X has been scaled and centered nicely, and so Z is XV. Let's say we choose the first Q of these. And then we're going to regress Y onto Z. That's basically it. As I said, basically PCRs, instead of regressing Y onto X, we regress Y onto Z. It's a little bit more complicated than that. We typically when we typically want an intercept, right? So when we wrote our design matrix previously, we had this column of ones, and the Z doesn't have this column of ones. So often, what we'll do is you would include a column of ones in the Z. So let's say often Z is really a column of ones, right, for our intercept term, basically includes the intercept, and then the rest of it is X times the first Q columns of V. And then we regress Y onto that. What does that mean? I.e., so this is all kind of parenthetically, kind of more details of implementation, but typically you'd actually include that column. I.e., right, we can get a regression coefficient through our nice regression formula. We call it gamma hat PCR, which is the kind of beta hat, but now we're just call it gamma, of regressing Y onto Z. And what's the formula? Z transpose Z inverse Z transpose Y. Most important formula in the class, probably. That and SVD. If you remember nothing else from this class, remember these two things. And so that would be the regression slope, the coefficient, right, from regressing Y onto Z. And what do we do then for prediction? This is step 3, prediction. If we want to predict on the training data, for example, Y hat for the training data is just X sorry, it's just what, z times gamma hat, all right? And that would be the PCR prediction for our training data. So the question comes, what do we do for new data? Notice here that this thing here, this gamma is an RQ. So I'm not calling it beta, I'm calling it gamma. It's a Q-dimensional thing, right? We've reduced our data down to a Q-dimensional Z. We have Q variables, now not Z variables. So gamma hat correspondingly has Q, or Q plus 1, however you want to think about it. If you include the intercept, it'd be Q plus 1, right? And so what do you do? Because how do you get a Z matrix, right? If I want to predict on some Y, let's say some testing Ys, how do I get that? Do I take the SVD of that? It could be a different SVD for, what if I just have one test value I want to predict on? Can I take an SVD of one value? So what you want to do here is you basically want to take the new data and you want to project it down into the subspace here. So basically what we've done is we've reduced our data down to the subspace, right? Using our training data, and then we predict there. And so for new data, we're going to project it down into the subspace, basically get the coordinates of the new data with respect to the subspace we learned, this principal component subspace, and then multiply by gamma. So let's say A is an n by p matrix, and this is going to be new data that we want to predict, right? I can't just multiply by gamma because it doesn't even fit. Gamma is Q-dimensional, this is P-dimensional. And let's assume, what do we want to assume? We're going to make a tilde. So let's say 0 is this. Step 1 is if A has columns, let's call them little a1 to little a p. So this is our new data. We basically need to go through all the steps that we did to the original X, including mean centering them, scaling them if we scaled them, projecting them down by V, and then multiplying by gamma. So first, we would basically take off, you'd say A1 minus X bar 1, right? Now X bar is the mean of our original training data. And you do this to all the columns. I subtract out X bar P, right? So I'm not subtracting off the means of the new data. I'm subtracting off those means. I'm doing the exact same thing I did in that training data. So let's say this is mean center. And we could say optionally rescale. So you don't want to rescale or mean center based on the new data's mean or standard deviation, because that might be different than the one you did for the training data. And so if you do a different procedure, it's not quite going to match up to the stuff you learned, right? So you just want to basically lockstep do those same things to the new data. So you subtract off the means of the original training data, you divide through by those standard deviations of that original training data. We can get a tilde, and then let's say 2 is we project it down onto the subspace, or we get the coordinates of our new data according to the subspace we have learned. So you kind of imagine this as a subspace you learn using the training data, and then that's the subspace it is. So you basically get the coordinates, or kind of project it down. So you look at, let's say, A tilde by V on the Q, something like that. So this is basically project into subspace. Notice we don't redo the SVD. If you do the SVD on this A, it might be different than the SVD of the other of the X's, right? You want to use the same thing, so so that basically that your gamma hat that you learned here corresponds to the right transformation of the data. Kind of more generally, like what if you had just like one sample you want to predict on? You're gonna learn a one-dimensional subspace. You can do SVD of one observation. It doesn't make sense. So the third step is then that y hat for our, say, testing data or our new data or unseen data is a tilde that's been projected down, and then we multiply by gamma hat. And that's it. Notice here, so that let me just stop for a second. So that's the whole procedure. I mean, it's really not a hard procedure. Basically, you take your original data, you might mean center it, you might rescale it, whatever. Just keep track of what you did. You do PCA on it, so you basically take the SVD, and then you just form those principal components of your training data, and you learn how to predict off that subspace, off that projected, that reduced dimension data. The idea being you basically reduce the number of variables in some way. So you've done some kind of variable selection. So this will work, right? If I have fewer observations than I have variables, right? Beta hat for a typical regression would be undefined, right? You would have an ill-posed problem if you had more covariates than you had observations. But if you do PCA, you just reduce the number of variables you have, and everything works out well, right? So the Z transpose is never going to be non-invertible. You're never going to run into those issues. So it's solving the kind of same problem that Ridge would have solved. You know, if you have two variables that are perfectly correlated, you know, PCA is going to kind of take an average of them or something like that, right? So it seems very much like Ridge, and it is. It's solving the same kind of problem. So then when you do your prediction, you just basically redo all the steps that you did. Notice here, I could pull off this. I could call this beta hat PCR. And this thing would be an RP, right? So this V is, let's say V1 to Q is, what's the dimensions of that? It is N by Q. Think about the SVD and why this says N rows. And gamma hat is in RQ. That can give us the dimension we want. What am I missing here? Q columns. No. What am I doing wrong here? V should be P by Q. There we go, right? As the aside here, right? If X is U dV transpose, X is N by P, U is N by N, and V is P by P. So the first Q columns of P will be P by Q, and so if we, and gamma hat, which is kind of the regression coefficient we learned from that subspace, is in R, and I can't write this up, is in RQ, then if I multiply them, I get something in RP. So, and what I have then, so my predicted is basically whatever my matrix is times some beta hat PCR. And this is so this A here is an N by P matrix. It might have been recentered and rescaled, but it's not a huge deal. And this beta hat, and in fact, we might add in the column of ones to A also. A side story. Let me say that. So typically, practicality, you're adding that column of ones like you would in an X in the design matrix, right? And this beta hat is going to be, basically an RP or RP plus 1 if I have my intercept term, right? And so this looks a lot like regression, right? Regression would be x beta hat. You can call x train beta hat. And so it's kind of like a regression. This is the beta hat, not in terms of that subspace, but basically in terms of the original full space. And I said that this all feels a lot like ridge regression because we're solving kind of the same problem where if you had too many variables in ridge regression, or you had things that are highly correlated, you might want to reduce them. You want to deal with the correlation in some ways. And PC regression is doing the same kind of thing, but it does, instead of penalizing the minimization problem, what PCR does is it reduces the variables into using clever linear combinations. But instead of this variable section I'm choosing individual one, it's taking these clever linear combinations to reduce the number of variables. And but in both cases, say if the number of samples was smaller than the number of covariates, X transpose X would not be invertible, right? The typical OLS regression would not work. So you might use ridge regression, or you could use PCA regression, because you in both those cases, they're going to constrain the problem or deal with the problem of a non-invertible X transpose X, or something that's maybe close to non-invertible. So is there a way we can formalize this comparison? So let's talk about what the comparison is to ridge regression. Because if you think back to ridge regression, the reason I introduced the SVD in the first lecture, because I wanted to talk about it in ridge regression, because I wanted to talk about it now in terms of PCA regression. And so you notice when we talked about ridge regression, you go back to that lecture, I talked about how it shrinks things, but it shrinks things according to what I call them the singular vectors in that point. Or you call them principal components now if you want. And now we've come up with a procedure that shrinks things according to that kind of scheme, or changes things according to that kind of scheme. So it seems like there should be some relation between these procedures based on the singular value decomposition. So let's first talk about ridge regression. So beta hat ridge, right? We said had the form X transpose X plus lambda I inverse X transpose Y. And so if X transpose X is not invertible, say if N is smaller than P, we're okay. Similarly for PCA regression, if N is smaller than P, well, let's just choose, do PCA and choose some Q that's smaller than N, and now we get a Z, for our regression. We basically form this Z thing so that we can actually calculate Z transpose Z inverse is well defined, right? And so that's the other way of solving this problem. So that's the beta hat ridge. And if I were to look at, let's take some new data, or whatever data, and let's just call it generically A, and A is N by P. And maybe we centered it, we've rescaled it, whatever we need to have done to it. Doesn't really matter. We've done it to everything, so it's all the same. And we can look at our prediction, our Y hat, which is A beta hat ridge. Right? And I can throw in some terms here. So I could throw in an A, I could throw in a V, let's say D inverse D V transpose. And I'm allowed to throw that in because this all will just be the identity matrix at the end of the day. D inverse by D, surely it's the identity matrix. V transpose, that's an orthogonal matrix, that's the identity matrix. So that doesn't actually change anything. And I'm going to call this thing A dot. Now V and D are the matrices from our SVD of our training data. So they might not be related, they may not be the exact same thing as if I did the SVD to A, I'm not necessarily going to get the same U and the same B, for example. And so this is our training data. But let's just call this thing A dot. And basically A dot is basically if I project A onto the V basis, onto that subspace, and let's say, and we rescale by singular values, by the elements of D, right? So D, of course, is this kind of faux diagonal matrix where it has sigmas down that main diagonal and zeros elsewhere. It has some kind of inverse, whatever. And so you basically AVD inverse is we take A, we kind of think about its coordinates in terms of this new basis of the space, and then we rescale the dimensions kind of according to the singular values. But if the rescaling is not as important, basically it's just a projection. It's kind of it's A under a different basis is all it is. And so if we consider dV transpose, I want to consider this dV transpose beta hat ridge, which is dV transpose x transpose x plus lambda I inverse x transpose y. And I did this calculation when we talked about ridge regression, dV transpose. X transpose x, if x is UdV transpose, this is VD squared B transpose plus lambda I inverse, and X transpose is VDU transpose Y. And I can bring these V's into the inverse here, but I got to bring the V out on this side, the V transpose on this side, and then I got to take their inverses. So I did this, I'll do it a little quick because I did it for the ridge. But if I bring those in here, I'll be able to get, I'm just going to get D squared plus lambda I. You can go back to the ridge lecture and think about why that is. It's just a bunch of transpositions, transpose their inverses for orthogonal matrices, blah, blah, blah. And then I'm going to get D, the U transpose, and the Y. And all of these, so this is a product of a bunch of, I guess there's an inverse in here, right? It's a bunch of diagonal things. This is just a diagonal matrix, and its elements are the singular value squared over the singular value squared plus lambda, right? So we talked about that for ridge. So that whole mess there is just a diagonal matrix. And so if I bring down my y hat now, y hat, it was basically this A thought about in the kind of original basis times V transpose beta hat ridge, or dV. There we go, we get this D. So it's basically A dot times, oh, I don't know, let's call this thing delta U transpose Y. And we can write this out as the sum from J goes 1 to P of the jth column of A dot times the jth element, whoops, the jth element of this diagonal matrix, like that, times Uj transpose Y. So that's just some linear algebra writing it out that way. And our interpretation of all of this is like A in my principal component basis. This is some weight. Let's call it, we don't want to use W again, do we? Call it delta I. And then this is basically how much, or the correlation between we said our U's are basically our principal components between PCs and Y. So all of this is when we predict with Ridge is we can think about, we can transform A into this principal component basis, and then we get kind of the coordinate of A in this PC basis. And if we ignore this weight for now, it's basically you get the coordinates of A in the PC basis, and then you multiply by the correlation between that principal component and Y, and you sum it up. If we ignore the weights, you would get exactly OLS regression, the exactly simple, the traditional regression, right? But what ridge regression does is it shrinks, it weights things. It's going to shrink, has a shrinkage factor, right? This thing is less than 1. It shrinks things according to the components, and it shrinks the smaller components more. So it's basically going to say, I'm going to downweight the contribution of the less important dimensions of my space, according to PCA or according to the SVD. So all this is basically, let's look at A in the coordinate of the PC basis, and we're going to multiply by the correlation between these PCs and Y, the thing we want to predict. And in the case of ridge regression, we're going to downweight the things that have small singular values, that have small variances. The unimportant principal components get downweighted. We can play the same kind of game. Let's say same game for PCR. And I'll do this pretty quickly, but here I can look at A times beta hat for my PCR. And we can play similar games where we can say A, B, D, inverse, D, D times B transpose times beta hat PCR, right? So something like that, right? Same game we played for bridge. And so we call this thing A star, or A dot, and then we get V transpose, and beta hat PCR was V1 to Q times gamma hat for our PCR. So A dot V transpose V1 to Q. And this thing was what? It was Z transpose Z inverse Z transpose Y. I'm going to get a little sloppy with notation here. And then calls me out on it, but the general story is true. And Z, of course, was V1 to Q. Was X times that. So we get an A dot, V transpose, this, and Z transpose Z, according to this, is basically V1 to Q transpose X times V1 to Q inverse, and Z transpose is V Q transpose X transpose Z. Okay. And we can think of this thing, X times this X V thing here, as basically being U1 to Q times D. Some caveats there, but basically that's what's happening. And as we saw before, X transpose X is, what did we get? V D squared V transpose, something like that. And so, okay, let's keep going a little bit more. This thing is now x transpose x, but we basically have the v's on each side, which are more or less going to cancel with these. And we're basically going to be left with dq squared. That's a little bit of a trick I'm playing here, but not bad, right? So basically when I multiply v1 to q by v, or v transpose, not quite the identity, but it's basically going to leave us with just that d squared there. That will be an inverse. And then this thing will basically give us dq. I guess I should have a q here, right? u1 to q transpose. Oops, that should not be a z on the end. That should be a y. So the notation's a little bit not great. And what am I missing here? I'm missing a d, right? And yeah, I think I'm just missing a d there, right? That should be a... Is that right? So that was d. Yep, that's a d that I didn't bring in there. So that should be a d to d, something like that. Yep. This is basically the identity matrix. Not quite, but again, small caveats that are not too important in feeling, and then it basically is this to the -2 something like this, and these things basically cancel out because you basically have d to the -2 and dq, d squared or something, right? So the subscripts are a little bit janky, but getting all the dimensions to work properly is a bit more. But in spirit, this is basically what's going on. And the proper notation is even more cumbersome, so let's not worry too much about it. But basically, this is in spirit what is happening here. And so you can try and work it out in full gory details. Basically, what we get here is we can write it again as a sum, j goes 1 to p, of basically of our a, j dot times some delta j u j transpose y. But instead of being p here, we're basically going to sum to q, right? Because I have only q columns I'm working with. And so I guess we can even ignore that delta, right? So it's just going to be something like this, right? And so the interpretation here is actually even a little simpler. It's basically the coordinate of the A with respect to the PCs. So we basically get the coordinate, and then we multiply by the correlation between that PC and Y, and then we sum all that up. Now, as I started to write out here, you can basically write this as a sum from 1 to P, where you have a weight, let's call it delta, but delta J is just going to be 1 if J is less than or equal to the number of components we're retaining, Q, and 0 otherwise. So it's a lot of linear algebra. It's a pretty advanced topic, but this is exactly the same form as ridge regression, right? If you look at ridge regression, this is what we're calling delta J, but it's the same exact form. It has a different weighting scheme. And the weighting scheme for PCA regression is basically to zero it out if you're above Q components and leave it alone if you're under Q. And this does some kind of more proportional where it scales all of them. So the picture that you can draw is that basically we have some scaling factor, we were calling it delta J, which is some number between 0 and 1. And for ridge, And this is like, so I guess, so some here we have Q over here, and we have like P over here. And ridge regression, I guess if 1 is here, ridge regression looks something like this. It scales these things something like that. So this is kind of what ridge does. It's going to scale everything a little bit less than 1. It's going to have these weights that are a little less than 1, but it's going to scale everything like that. PCA regression, basically flat line, says all the way, you're going to weight everything at 1 up until Q, and then you're going to weight it all at 0. So that is the weighting scheme of PCA regression. So it's a little bit of an advanced topic. I mean, it's not the kind of thing I would expect you to recapitulate on an exam. And I didn't do the math in all the full gory details because, again, it's just a little bit cumbersome notationally. But I think it's really important to point out the connections between these, because otherwise you would go away from this class thinking this ridge regression over here has no relation to PCA regression. We just have a bag of techniques. But there's a real strong relationship between these things. And in some ways, they're just kind of different weighting schemes for this, where you just basically project your data down onto the principal components, and then you sum it back up with some kind of weighting scheme. And that, PCA regression is a really hard binary weighting scheme. In ridge regression, you can see it's a smoother version of PCA regression. The last thing I'll say in the last minute or so here is that if my X is full rank, that is, X transpose X is invertible, which is possible a case we care about. We say ridge or PCA regression really are nice if we have a non-full rank X. Either we have more covariates than we have observations, and so X transpose X isn't invertible, or we have like highly correlated or perfectly correlated covariates. In the case where we don't have that, as lambda goes to 0 for our ridge regression, beta hat ridge is going to go to our OLS estimator, right? It's just going to, if you set lambda equal to 0, it wouldn't penalize at all. You just create our normal regression estimator. Similarly, as Q goes to, what were we calling it? R, which is the rank of X, I guess. Let's say P, which is the rank of X. Then we'll get beta hat PCR will go to beta hat OLS. We're basically going to get the same beta hats here. However, if X isn't full rank, we're not going to get that similar behavior. We're not going to get these converging to the OLS estimator because the OLS estimator isn't unique if X isn't full rank. However, as lambda goes to 0, the ridge regression estimator, it won't converge to the OLS estimator because the OLS estimator isn't unique. There is no thing to converge to. Instead, it will converge to the PCR estimator with Q is equal to the rank of X. So in the simple case where everything's nice and X is full of rank, they're both going to converge to the same thing. If you send Q to the rank to P, it gives you the OLS, and ridge, as you send lambda to 0, it'll give you OLS. In the case where X is not full rank, the OLS estimator is not unique. We're going to need to use something like ridge or use something like PCR. And in this case, as I send lambda to 0, the ridge estimator is actually going to converge to the PCA regression estimator, where we choose Q to be as high as we possibly can. It can't be P because X is not full rank, but it can be whatever as large as it can be. So in some ways, these estimators are all really intimately related to each other. So we'll stop there, and we'll look at this in some code. This is a little bit of a more technical lecture, but I think it's important to at least give you a flavor of some of the nice theory we can do if you learn linear algebra and how some of these things actually fit together with each other.